Hi, everybody. I am half the team behind a tool called pgMustard. So we visualize, explain, analyze output, and provide advice on perhaps where the problem might be or what might be possible to speed it up. So as a result, I've spent a lot of the last few years looking into explain plans, but also behind the scenes. So yeah, hopefully I'm here to share some of that with you today. My background is in product management, a lot of that in database tools. So obviously pgMustard, but also previously at a company called Redgate, where I spent a lot of time working on SQL Server and Oracle tools, as well as MySQL before Postgres. Below there, you can see my contact details, as well as the first link there is a link to a glossary of terms that we put together last year. Spent a lot of time on that, documenting every operation, every field that we've come across, mostly because we couldn't find good explanations of them elsewhere. So hopefully that will be helpful to some of you as well, perhaps as a reference. Wonderful. So today we are going to pick up where other talks leave off. So I've seen a lot of good introduction talks and blog posts about Explain, and they cover a lot in an hour or so, but it's such a deep topic that I wanted the next hour of that. I wanted them slightly beyond the basics. So hopefully this is that talk. Specifically, we are going to cover some of the arithmetic that you need to be able to do to calculate, for example, per operation timings or the number of rows returned at each stage, as well as some less spoken about and maybe slightly rarer issues that you can spot through Explain that maybe not everybody realizes that you can. If you are interested in the basics, then my recommendations are, as always, the Postgres documentation. So the guide's really good. It gives quite a brief introduction to Explain and then Explain Analyze. For a bit more information, I thought the ThoughtBot blog was really good. There's a post that they've kept up to date called Reading, Explain, Analyze. And then the talk I think is best for the basics is one from about 2015, 2016 time. I think he gave it a few times. It was by Josh Burkus, and like a lot of them, it's called Explaining Explain. Even though it's a few years old now, the topic, it's still super relevant. Everything in there still makes perfect sense, and it's still a really good introduction. So the aim here today is to pick up from that. Great. So yeah, specifically, the arithmetic's important for working out why is this query slow, and trying to do that as quickly as possible, and not missing something or being taken in the wrong direction. And then the second half is going to be, so we now kind of can see which part is slow, but is there anything we can do about it? And if so, what? So we're going to go into some of those. Brilliant. So yeah, firstly, a disclaimer. One of the biggest challenges with explain plans is that they can be very text heavy, which doesn't lend them very nicely to slides. So I have edited them mostly for space, but also for clarity and anonymization. I have checked them a lot of times now, but it is still possible that I've made a mistake in editing them. So apologies in advance if I have. Great. So diving into the arithmetic, the first thing I'm going to mention is to keep an eye out for loops. So this could be, and I'll show you an example in a moment, a nested loop where one of the operations is being looped over multiple times. Many of the stats that you'll see reported and that you probably have covered in previous explain talks, things like costs, rows, and the timings, are reported as a per loop average. So that's a mean. Now that's really useful in a lot of ways, and it's how the planner thinks, but it can cause some issues. Costs and timings are fairly specific. So costs are measured to 2 decimal places in an arbitrary unit, but they tend to be, that tends to not be a big issue. And timings are 3 decimal places in milliseconds. So again, if you're around the 0.000 milliseconds, it's probably not the slow part of your query. So rounding doesn't tend to be an issue there, but rows are an integer. So the difference between being rounded to 0 and being rounded to 1 can be quite dramatic when you're looking at a lot of loops. Equally, even 1 to 2 can be quite a large difference. So there are some potential rounding issues to be aware of, especially in the row department. So let's look at an actual example, and you can already see what I mean by the editing. So in this case, I've squished things onto multiple lines where they would normally be one long line. And I've put some of the numbers we're going to be looking at here in bold. So as usual with explain plans, we read kind of inside to out. So let's look at those children operations, and the index only scan, we can see that it's returning 9 rows across one loop. And then for each of those, we're then doing an index scan. So we can see that loops 9, and those are returning on average, so to the nearest integer, 10 rows per loop. If we look at the nested loop operation at the top, the parent operation, we can see that 86 rows are being returned in total. So you can already see a slight discrepancy between that number we could get from multiplying the averaged number of rows, so the 9 times the 10 versus the 86. We know the nested loop isn't discarding any rows in this case, so you can see already where rounding starts to come in. It's not going to trip you up in this simple example, but you can start to see where it can be problematic. Wonderful. So in related news, we also have threads. So parallelism can make some of this arithmetic quite tricky as well. Again, those statistics I mentioned before are a per thread average, and that's convenient since their threads are also displayed as loops in explain analyze. You can get more information on the worker threads by using verbose. So specifically explain analyze verbose in parentheses or brackets. That's a parameter. I tend to recommend using quite a lot of parameters for explain. So the buffers one is particularly useful, but verbose is useful when you're looking at threads specifically, as well as a few other things. Importantly, the loops, you quite often see a discrepancy of 1 between the number of loops and the number of workers, and that's because the main thread is counted as a thread, as a loop, but it isn't reported in the statistics. And I'll show you in a moment how we can calculate the leader thread's contribution, which is quite important because when it is doing work, it quite often does more than its fair share of the work. Great, so this is again, simplified, edited example. And the important numbers here to look out for, again in bold, we can see the parallel sequential scan being run across 3 loops, threads in this case. Now you'd be forgiven, I think, on first glance for thinking this whole sequential scan was returning, 63,600 rows. But in fact, that needs to be multiplied by your 3, and it's more like 191,000 rows in total. Now that becomes a bit more obvious once you include the verbose and the worker numbers below, and you can see that each of those 2 are returning fewer rows than the average above, which means the leader must be returning more. And you can see from taking those numbers away from that average times 3, it's about 76,000. Now that's interesting when it comes to rows, but it can be really important when it comes to timings. So I haven't highlighted it here, but you can see that those 2 workers were taking about 66 milliseconds, and the average per thread was closer to 72 milliseconds. Now that's about 5 milliseconds higher than the 2 workers, which means the leader is probably taking over 80 milliseconds in total. Now, that might not seem that important, but it's quite a big discrepancy versus 70. And if you're then subtracting that from a parent operation, you can start to see where, if you're not careful around these calculations, and if you naively take the average away from the parent, you might not be getting quite the true picture on where the time's going. Wonderful. So I mentioned buffers briefly just then. If we include that as a parameter as well when we're requesting explain analyze, we'll also get the number of blocks read or written at each stage. Importantly, though, unlike the other numbers we've mentioned briefly, this is not a per loop average. So this is a total at the operation level. But like the others, it is inclusive of its children. So a parent operation reporting a certain number of buffers, in order to work out if the parent has been responsible for any more reads or writes, you need to subtract the numbers from the children. Luckily, this is a bit simpler than before because we don't need to multiply by loops or take anything else into account. So in the simplest case, we're back to that nested loop example from earlier. You can see that that initial index only scan we're doing is reading 4 blocks. So that's the shared hit statistic there. That means they're coming from the buffer cache. And for each of those, we're not doing, so for each of those, the index scan is not doing 101 blocks of reads. That's across all 9 loops as a total. And we can then see that the nested loop above is not doing any additional reads as expected for a nested loop. So hopefully that's nice and simple. On the slightly more complex side of things, we have timings. So as I mentioned briefly, these are per loop, per thread numbers and inclusive of children. Now, the per node times can get tricky, even for tools. So we've spent quite a lot of time on this for pgMustard, and it's nice to see, I think, some other tools starting to as well, which is really cool. But yeah, I'm going to show you where it can get tricky and therefore where to be maybe a little bit suspicious of what you're being told, even if you are already using tools to do this. But first, a simple example. So again, we've gone with the, I've tried to highlight the important numbers here in bold. You probably already covered previously, but that first time being reported is the startup time for the operation, and then the second time after the 2 dots is the total time. So the first one could be thought of as the time taken to return the first row, and the second time is the time taken to return all of the rows. So in this case, you can see, if we again go inside out, that the index only scan is reporting that it took 0.019 milliseconds. The index scan, we can see 0.030 milliseconds, which looks a lot less than the nested loop total above, until we remember we need to multiply that by the number of loops. Once we've done that, we can see that it is in fact responsible for the majority of the time here, and the nested loop is only adding a small overhead of 0.079 milliseconds in total. Great, so that was the simpler case. This is the simplest version of a slightly more complicated case, and one of a few, but I think CTEs in general and recursive CTEs, especially those where the query references them more than once, so taking advantage of a Postgres optimization that lets it materialize that, that can get tricky in terms of timings. Now, we're going to look at a really simple example here where it's fairly clear to a human where the timing is going. That's deliberate, and credit to Felix Geisendorfer for this example. He was great to talk to when we were looking at how we wanted to apportion time correctly in these cases, or at least maybe not correctly, but in a way that's most helpful performance-wise. So yes, so this is a fairly simple example where we're using a function to make Postgres sleep for 100 milliseconds, 200 milliseconds, and then referring it to it twice in the query below. So looking at the query plan for that, it's fairly clear that the whole thing is only taking 300 milliseconds. But if we were to use the rudimentary logic we've talked about so far, where we sum those or subtract those from the parent, the children total 300 plus 100 plus 200 milliseconds here, so a total of 600. Now that's due to some double counting, and each one on their own makes sense, but to a tool it needs to work out which one do you want to point at for having taken the majority of the time, or which one do you want to subtract from which? So yeah, that could be a conference talk in its own right, and part of me hopes that Felix or the other half of pgMustard, Dave, give that talk one day. But for anybody super interested in ways you can do this in more complex cases, I highly recommend Felix's site, flameexplain.com, and his post specifically titled Correction. He goes into that in a bit more detail on how he views it and how he calculates it. So speaking of tools, there are so many tools that can help you visualize, explain, analyze output. A lot of IDEs offer them as well, way more than I could fit on one slide. But here are some of the more popular ones that have come across. There's the original, or a very old one, but has been kept wonderfully up to date by Depez, so explain.depez.com. You'll see that all over the place in terms of on IRC and Slack and places. It focuses it preserves the text format, but also tries to highlight some of the problematic areas and the timings, some of the timings that we talked about. Delibo is similar, but much more visible. Much more visual. That's based on a lot of you might be familiar with a tool by Alex Tatians called PEV. This is effectively, they've called it PEV2 even. There's a Russian, or it was Russian language only, a tool by Tensor that's now in English, but that's the one I'm least familiar with. So if anybody here uses that a lot and likes anything particularly about it, that would be wonderful to hear about. So I'm not as familiar with that one, but it looks great. And then Flame Explain is much newer, but that's by Felix, and he's really, really focused on trying to get these per operation timings accurate. And the reason for that is, like us, he's got a version of a flame graph in his tool, and that only makes sense if you're looking at things on a per operation level. So that becomes really important. And then pgMustard's the one I work on. So part of the tool is a timing chart that is effectively a flame chart viewed from flame graph viewed from above or below, I guess. And yeah, we try to give advice as well, but it's a very visual tool. Brilliant. So once you've got an idea of the, in summary, I would advise checking the arithmetic and double checking, because one mistake, one missed loops number, and you could be really far out on where you think the time's going. The CTEs, be particularly cautious or maybe suspicious when you've got CTEs. And when I'm in doubt, I do check in a second tool and just see how are they apportioning times here. Is it massively different? One case I didn't go into, but I saw recently somebody having problems with was a tool not calculating partitions or subtracting partitions correctly from I think it was a gather or maybe a gather merge operation. So anytime where there's a lot of subtraction or anything subtle around CTEs, be a bit suspicious and maybe check in a second one. That would be my advice. Brilliant. So on to the second half, we're going to have a look at some of the less common issues in detail. But first, the three that pretty much every talk or blog post will at some point mention are looking out for sequential scans. Now, I would add to that, and it will become clear in a moment why, but sequential scans on their own, I think, get a bit of a bad rap. They're the fastest way of getting most of the rows from a table. it's only with your filter, or if you are or you'll later filter down to a much smaller subset of those rows, that it makes sense to think about indexing. So yeah, I would recommend looking out for those large filters, specifically on any operation, not necessarily just on sequential scans. And we'll look at an example of that in a moment. The second thing that most cover, because it's really common cause of Postgres picking the wrong plan, is if the row estimates are off. And generally they advise if it's off by a lot. I would add to that even if it's off by a small amount, but it's in your critical path or on part of your slowest subtree, they can be interesting to try to get better. And there are lots of ways that you can try to do that, but I think it's pretty well covered elsewhere, so we're not going to go into an example here. And then the third one that's fairly well covered elsewhere are, for example, sorts and hashes that spill to disk or happen on disk rather than in memory. So perhaps the solution there is reducing the memory requirements, so maybe doing it on fewer rows or fewer columns, filtering down sooner, that kind of thing. But the other thing that people often mention is increasing work mem, especially if it's still set to the default of 4 megabytes. Great, so let's look at some slightly rarer ones, or ones that aren't as well covered elsewhere at least. This one, the short version of an inefficient index scan is what I'm calling it, is an index scan where you're scanning a lot of rows still to return relatively few. So you'll see those being filtered out. There's a couple of ways Postgres can report that, and we'll look into one in a moment. Importantly, in fact, crucially for these index scans, it's worth remembering that these filters are a per loop average again. And because they are a number of rows, they're an integer, and there can be quite severe rounding issues, especially around 0 and 1 rows per loop. This is a simpler example than that, though, where we only have one loop, but you can still see a very inefficient index scan. So the rows removed by filter there is the super important thing to be looking out for. We can see here that that's over 3 million rows being removed by this filter to return, as we can see above, 1,000 rows. So the short version here is, just because your query is using an index doesn't mean it's fast, it definitely doesn't mean it's optimal. If you can work out a different index or different way of getting to those 1,000 rows that you want without having to scan the other 3,000, chances are it'll be a lot faster. So yeah, if you want to put a number to it, you could say that for this query, this index is 0.03% efficient. And yeah, my advice here again would be, do keep an eye out for that loops number. So even if your rows removed by filter is 1 or even sometimes 0, but yeah, let's say even if it's 1 and your loops number is really high, that can be problematic as well. Great. So the second issue that I'm going to go through today is the concept of filtering rows late. So if we go through our query plan kind of bottom to top or inside out, this is kind of in the top left. So if you see a lot of rows disappearing quite late in the process, perhaps through a limit, but you're still having to do a lot of that work up front, chances are there's a different way to get that data, or that if you can work out a different way to get the rows that you want without having to do as much work, chances are you can do that a lot quicker. So yeah, those row calculations that we've done in the first part of the talk become really important for spotting these. Look out for a lot of rows being discarded, very similar to the tip before, and yeah, if you can, filter earlier. So super simple example here, and this would have been caused by a limit operation from memory, where you're still, because it's a sort, because the data is not coming back sorted, it still needs to get all of that data, then sort it, probably a top-end heap sort in this case, before returning the top 100. So if you can work out a way of getting that data sorted earlier, chances are it'll be a huge amount faster. So yeah, naturally, an exception to this is an operation that's designed to do exactly this. So if it's an aggregation, then you're going to have to read a lot of rows in order to provide relatively few. So yeah, I'm not talking about that in this case. Wonderful. Next one requires you to use that buffers parameter that we were talking about earlier. So at minimum, explain, analyze buffers. Is if you're reading a lot of data, and specifically for the amount that you're returning. Again, caveat: if you want to be doing an aggregation, this might not be. You might be willing to accept this, but in other cases, it's a real big flag for an inefficiency. So yeah, lots of data being read for the amount returned, and one of the things that this can be a sign of is table or index bloat. And in order to calculate or get a feel for how much data we're talking about, it's worth knowing what block size you use. Pretty much everybody, I believe, uses the default of 8 kilobytes. Wonderful. So, simple example. Here is an index scan, and you can see a lot of loops, interestingly. One row returned per loop, and then the width value is an estimated average width in bytes. So we have a few caveats here. So that width is estimated and the rows number is rounded, and it could be anything from 0.5 rows per loop up to 1.5 rows per loop, which is quite a big difference when we consider how many loops we're talking about here. But luckily, the buffers numbers are not a per loop average. So in this case, we can clearly see those. Now, to get an idea of the data read, we can sum those together, times it by 8 kilobytes, and we see it's about 10 gigabytes in total. But the amount we're returning, if we times that single row by the number of loops times the 8 bytes, is only 2 megabytes. So this is a really good sign that there's likely a way more efficient way of doing this. It might not be an option for you, or it might be something to consider down the line. It might not be something you can just optimize just for this query, but it's a sign that there's something inefficient going on, or possibly a sign of bloat. Wonderful. Next are lossy bitmap scans. So you're probably aware of bitmap heap scans, bitmap index scans. It's a really cool feature in Postgres that allows it to scan one or more indexes and then keep pointers to the rows that it needs to look up in a sequential scan. It's kind of an in-between between an index scan and a sequential scan that's really good for certain patterns. And yeah, if it's the concept of it being lossy is if it can no longer, within work mem, keep a pointer to every tuple ID or each row. So it instead reverts to keeping pointers to the blocks that it needs to. So therefore, it needs to keep fewer of those so that it still fits in work mem. So we'll see these as lossy blocks, and I'll show you an example in a moment, but it's worth remembering these are not a per loop average, like buffers. So in this example, we can see the lossy, it's the heap blocks lossy that we're worried about. And as you can see, we still get some exact pointers. So unlike a sort, for example, this can be done partially in memory, so work mem, as work mem scales, you'll get a less and less lossy heap scan or bitmap heap scan. So yeah, this is an interesting one, but like sorts and hashes that we've discussed before, if you can reduce the amount of work in the first place, that's a better option rather than increasing the memory available. Great, so in this specific example, you can see that we are returning 3.85 million rows, but in order to do so, we're also scanning another 5.9 million that we're later removing because we brought them in because they were in the blocks that we wanted to look at, but they don't meet the condition. So in this case, the lossy blocks are a huge proportion of the total blocks, 99% in this case, but beyond that, I believe. And then the extra, we've read in 6 million, so 60% roughly of the total are being read in and tossed away. So hugely inefficient. Chances are, if you can make this better or make there be fewer, either do less work or get it done in memory, chances are it could be quite a lot faster. Wonderful. The next issue is if you're doing an index-only scan, that is no longer index-only, so it still needs to go to the heap. Now, this happens if the visibility map suggests that that block has since changed, since maybe the last time you vacuumed, or last time vacuum was able to reset that bit in the visibility map. But the short version is this is a performance issue, because instead of only having to check in the index for the data, it's had to go to the heap. Maybe if you're doing a lot of index-only scans and you're only getting 1 or 2 heap fetches, that's probably not an issue. But it's when they're a large proportion of the total that I'd recommend taking a look. So here's an example, and this is going to also be an example of where that rows equals 0, and that being a rounded integer is problematic. So the thing to look out for is that heap fetches number. We can see 19,160 heap fetches. Now, we don't know exactly how many rows this index-only scan was returning just from this operation, but it's somewhere in the region of, well, I've put an estimate here, or sorry, a maximum. It could be up to 0.5 rows per loop, so up to 43,800 rows. The time, again, but the time we can get a much closer number for, it's a 0.037 milliseconds times that loops number. It gives us about 3.2 seconds, or 3,200 milliseconds. And the heap fetches, therefore, are at least 44% of the total rows. Could be a lot higher. Could even be 100%. But we already know that that's probably a problem. It's more than a few, and there's a chance this could be quite a lot faster if it wasn't having to do that. Great. So the next 3 I'm going to go through, I think the last 3 I've got are all things that appear in the summary section of the explain output, so right at the bottom of the query plan. You'll probably be used to reading query plans inside out anyway, but I would additionally add the advice of going straight to that bottom section and seeing if there's a dominant issue in those, just because it might avoid you having to read especially for a complex query plan, it might avoid you having to do a lot of work looking at the rest of the query plan. So one of those is planning time. And something, yes, a couple of little things to be aware of here. If you're only ever looking at queries that have really fast planning time, you'd be excused for thinking that it was included in the execution time. Now, I see this come up a lot for fast queries, people talking about this query only took 0.1 milliseconds. And you see above, you see execution time 0.1 milliseconds, but planning time 0.2 milliseconds. Now, it's tiny, but really in my head, that query's taken 0.3 milliseconds in total. So summing those together is a more, in my opinion, more appropriate total for the query. And then so you'll see that it will become obvious once the planning time is more than 50% of the total. One last caveat, for anybody using auto-explain, you might have noticed that you don't get planning time back as part of that. So this kind of issue cannot be spotted through auto-explain. So if you're ever in a situation where there's a big discrepancy between what you're seeing if you run explain manually and what you're seeing in the logs, you might have missed that it's planning time dominated. Great, so this is a super simple example, possibly the most edited of all of them, but it's just an example where planning time is a huge proportion of the total. And if you look above in the query plan, you can see where the rest of the time, the 11 milliseconds in this case, went. But there's very little benefit to speeding that up, and you're better off trying to work out why is it spending nearly 28 milliseconds planning. Great. The second of the three that you can see in that summary section at the bottom is JIT, or just-in-time compilation. So this was added in Postgres 10, but turned on by default from Postgres 12 onwards. So the idea of the feature is on average to save you time, but for some workloads, or in some cases, it can be the biggest bottleneck or the biggest problem in your query. So depending on your workload, you may even want to turn it off. I've seen some extension providers recommending that for their customers. But the way to spot it is looking at the bottom of the query plan. So crucially though, unlike planning time, JIT is included in the execution time of the operations above it. And yeah, so that's something to be aware of. So here's another summary section of a query plan. You can see that the execution time is just over 5 seconds, and the planning time is only 9 milliseconds, so not an issue in this case. But if we dive into that JIT section and jump straight to the end, which is the total, we can see that more than half the time, more than half of that execution time, or even the total time, is could be accounted for through JIT alone. So whilst you might be able to spot some optimizations you can do in the tree above, this is probably your biggest problem. Yes, and if you happen to miss that, or if for some reason you're turning summary off for the query plan in question, or maybe you've been given it by somebody else, and they've trimmed that to be helpful, this is another way you can spot that JIT that JIT might be the dominant issue. If you spot a really suspicious startup time, so remember that's the time taken to return the first row of an operation. So this example here is being taken from the example before. So it's a real world example we saw that's been anonymized. The actual time here is super suspicious. So we've got a sequential scan on a very small table. We're expecting it to return 72 rows. It only returns 54. The total number of blocks read is 3. So it's 24 kilobytes of reads, and it's taking 2.2 seconds to get started. That's, in this case, that was due to JIT, and I've seen this pattern a few times. So yeah, hopefully that helps a few of you if you ever aren't able to see the JIT in the summary section, or if you forget to check it at that one time. Great, and then the last of the three that you can spot from the summary section are any triggers, any trigger timings. So if you only ever, so first thing to note is, even if you don't use triggers explicitly, chances are you are behind the scenes for things like foreign keys or any other constraints. So you might see it as a result of that. And something I haven't included here, but if you're using explain analyze verbose, you'll get the trigger names as well, which I find particularly useful, because you can see, for example, if it's a constraint by the name of those. Great. So there at the end, there are total across all calls, which is obvious once there's a performance issue, so I'm not going to spend a lot of time on. But if you see a very small time, even if it has a lot of calls, it's not a problem, because that small time is the total across all of them. And then one other subtle thing that probably won't matter to you, as but is a thing that tools can get tripped up by, is that before triggers and after triggers are naturally accounted for differently when it comes to the timings. So the after triggers are not included in the first operation's time, but they are included in the total execution time. Any before triggers are also accounted for in that top parent or root operation. So unfortunately, there's no way of telling programmatically as a tool whether a trigger is before trigger or an after trigger. Sometimes you can infer it, but that's something that tools might struggle with in terms of telling you exactly which operations are responsible for how much time. Great. So as I mentioned, here's a trigger name that's come from running for Bose. So we can see RI, so referential integrity, underscore constraint trigger. And then that's taking a total of 83 seconds or 83,000 milliseconds across a lot of calls, 2 million calls. That's a huge proportion, or 95% of the total time for this query. Definitely the dominant issue, and very little point looking at the rest of the query plan, except to work out which constraint is this. The most common place we see this is in deletes of a lot of rows where the foreign key in question has not been indexed. So you probably all know that foreign keys in Postgres aren't indexed by default. So yeah, that's the most common place we see this, but it obviously can appear elsewhere as well. Great. So in summary, for the rarer issues, I recommend checking that summary section first before you do anything else, just in case you spot a dominant issue in there and can avoid the rest of the time spent analyzing it. Look out for all of the things I mentioned, or bear in mind that just because it's not got a sequential scan with a large filter, or you can't spot any operations on disk, or you can't see any really bad row estimates, don't give up. There's a lot of other things you can look out for: filters, rechecks, lossy blocks, heap fetches, even trying to work out how much data is being read at each stage for the amount returned. So yeah, that's not exhaustive. There are a few others as well that we look out for and we want to point out in future. And yeah, as I mentioned, there are tools to help with this kind of thing. And if you've spent quite a while on it and still stuck, there's a huge number of Postgres communities, including the performance mailing list, that we found really helpful and got a lot of ideas from. On that note, the last link here is particularly helpful. So it's advice on how to ask for help when you've got a slow query. But as a result, it's also a really good debugging process. So in gathering the information you need to help others, there's a decent chance you'll spot what the problem was yourself. I suspect that's not an accident, but it is really helpful when people have followed that, and then the community can normally help them really quickly. The other two links here I've mentioned previously, the quirk correction post by Felix around especially useful for CTE timing calculations, and the explain docs or glossary that we spent a lot of time on last year. Probably don't want to read through that. It'll probably be pretty dull read, but a really good reference guide if there's ever an operation you spot that you've not heard of before, or you want to check whether one of these statistics that we've been talking about is per loop, whether it's an average, or we've also linked to things like the Postgres source code or other guides on or like maybe even Stack Overflow posts that we found that have been helpful. So hopefully that'll be a good resource for you. Yeah, I think we're going to go live for some questions in a moment, but if you are watching this afterwards, or if you'd prefer to do it privately, that's my email address. Very well, contact me, and that's my handle on pretty much all of the Postgres community sites. Cool, I think that's it. Thank you.
So, thank you, Michael. That was a great talk.
Thank you so much.
I would say very precise and very methodical as usually, but probably it's the only way to explain. a bit of questions to you. So for many people, starting with explain is sort of the task when they do not know where to go, from which point to start, which queries should be explained. Do you have some advice how to work with this? So from which point to start?
Yes, so well, I think it's a really good point that explain can only really help you once you know which queries which query you want to look into, or which query is problematic for you. So it can help you go from this query is slow to what can I do about it. In terms of actually working out which query is slow, you're probably better than me. But my understanding is there are if you don't have pgstat statements already installed, that's almost a must for people, and that can help you look at your top 10 queries by total execution time. And there's a chance that some in there are optimized, but there's a good chance that some in there aren't. And that seems to be a particularly popular way. But yeah, otherwise there's a lot of monitoring tools, aren't there? And I think there's even an alternative to pgstat statements by the team at Pacona that looks really interesting. But I'd be interested in your thoughts on that as well.
Yeah, well, I always trying to figure out that myself, because people keep asking those questions, and if people starting to take a look on the database with lots of complexity queries, it's just a bit strange to try to optimize everything, because you do not have all the time in the world to do this. So yeah, basically I'm always tending to start with some top queries, and then this top changes drastically after first optimizations. So it's usually like this. We have rather a couple of comments instead of questions, which are saying that's very good talk, and thanking you about this in our YouTube chat.
Thank you.
Another common question, actually, are you lacking some instruments in PostgreSQL explain? So are there some things which could be improved, some functionality which is not there and could be probably be better?
Always, right? We're incredibly grateful to the people that are responsible for the planner, and the Postgres team's incredible. We've seen some talks recently by Robert Haas and Peter. I'm not going to try and pronounce his second name, but yeah. As somebody with a difficult to pronounce second name, I can sympathize. But yeah, so we love, yeah, right. I'm in the right crowd for that. Yes, there is a really good patch that I think needs some extra reviews, but I'm not sure. I think hopefully it will make Postgres 15. But somebody is working on giving you a max and min and total number of rows per loop. So it's not a per loop average anymore. So I think that would, a lot of the caveats I gave in that talk were around looking out for row numbers that have been averaged and might be hiding some important information. I think that would be added with the verbose parameter. That's the patch that's in there at the moment. I think that would be incredibly helpful, especially for tools, but also for humans. And in terms of other things, yeah, I have to think about it. I think we haven't spotted many things that we're frustrated by. There is one. There's if you're on a system with a really expensive system clock lookup, you can end up with timings having quite a high overhead. And I think there's some people thinking about how you could reduce that even on systems with that high overhead. But I think most modern systems don't have it. So my understanding is it might be something people are more scared of than it is true in reality. But in specific cases, it can be very misleading.
Mm-hmm. Yeah, thanks. That's actually interesting. Yeah. I probably always thinking if we can have some sort of trace information more than buffers, like wait events, things in explain. But it's usually always connected to things you mentioned. That's clock thing became extremely expensive in this regard. Yeah. Okay, so it looks like we do not have any more questions, but we have one another thank you. So people appreciate this. But anyway, we invite you to the Q&A channel in Slack, just in case if anyone hesitate to ask things, and probably people would ask further questions more privately on the credentials you gave them. Thank you. That was an excellent talk, as I told already. And we make a short pause before we welcome our last speaker, Bruce Momjan, and we'll be back soon.
Thank you so much. Thank you.